Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 3 of the Invariant Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. This is the problem we have today. We want to find all positive integers m such that for any positive integer n, this expression here, which is the sum from k equals 1 to 9 of k squared plus k raised to the power of n minus 9 times 10 to the n, is coprime to m. So in other words, we want to find all positive integers m such that no matter which positive integer n we choose, this expression here, evaluated at that value of n, is coprime to m. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so we're going to use a few different techniques to solve this problem, and what I want to do first is focus on prime numbers. And here's why. If m wasn't a prime number, say it was p1 times r, where r was some number which is at least 2, well then what we could do, and p1 is a prime, sorry, well if this guy here, this expression, the sum from k equals 1 to 9 of k squared plus k to the n minus 9 times 10 to the n, if that was a multiple of p1, well then certainly the greatest common divisor of these two guys here would be at least p1, and so wouldn't be 1. So we only really need to focus on prime numbers, and for now, and we'll see why in just a second, for now we're going to focus on primes which are at least, bigger than 9, so that means that they must be at least 11. So let p be a prime which is bigger than or equal to 11. And now what I claim is that this expression here, there exists some value of n such that this expression here, evaluated at that n, is going to be a multiple of p. So I actually claim that that holds for n equals p minus 2. So for now we're going to define n to be p minus 2, and we're going to prove that this guy here is a multiple of p for that value of n. And then what will that tell us? Well, that will tell us that if we choose if we want that this expression to hold true for all, if we have a value of m and we want this guy here to, to be, the greatest common divisor between m and this expression here to always be 1, regardless of what n is, then we'll need m to have prime divisors which don't include any primes which are at least 11. So in other words, when we look at the prime decomposition of m, it will only contain the primes 2, 3, 5, or 7. It won't contain any primes bigger than 11, because if it did, we can look at the case n equals p minus 2 and show that this guy here would be a multiple of p, and m is a multiple of p, so that means that their greatest common divisor will be at least p, and thus not 1. Cool. But of course I've got to prove that this guy here is a multiple of p for n equals p minus 2 and p being at least 11. Let's see why. Firstly, let's just write out this expression here. So we've got the sum from k equals 1 to 9 of k squared plus k to the n, but n here is just p minus 2, and then we're doing minus 9 times 10 to the p minus 2. Now what we're going to do is use Fermat's little theorem, which says that a to the p minus 1 is congruent to 1 mod p, when a is coprime to p. So in other words, a is not a multiple of p. So we're not going to prove that, but that is Fermat's little theorem, a very well-known theorem. What we're going to do is use that and say that, well, because k is between 1 and 9, we can think of k squared plus k as just k times k plus 1. And now it's something between 1 and 9 multiplied by something between 2 and 10. So certainly the prime factors of this guy here are going to be, going to consist of prime numbers which are at most 10. So in other words, 2, 3, 5, or 7. And that's kind of why we've chosen, for this kind of lemma, I guess, for p to be at least 11. So we know that this guy here is never going to be a multiple of p. In other words, it's coprime to p, so we can apply Fermat's little theorem. And so that's going to tell us that if we write this p minus 2 as p minus 1 minus 1, this thing here is going to be congruent to the sum from k equals 1 to 9. Now we can write this as just 1 mod p. So it's going to be 1 times, well, we've still got a minus 1 here, so 1 times k plus 1 inverse, and then minus 9 times, and then we can do the exact same thing here, because 10 here is just 2 times 5, so it's not going to be a multiple of p, it's going to be coprime to p. So again, we can use Fermat's little theorem and say that that is just 9 times 10 inverse, like so. So we get that this guy here is congruent to this guy here, and of course 1 times it is just it. So we've got the sum from k equals 1 to 9 of k plus 1 inverse minus 9 times 10 inverse. Now what we're going to do is look at this guy here and see if we can do some nice algebra with it. So we have that k plus 1, oopsie daisy, inverse. What is that equal to? Well, that's equal to k plus 1 inverse times k inverse, just expanding, sort of, yeah. And this guy here, I'm going to write as k plus 1 minus k times k plus 1 inverse times k inverse, because of course this guy here is just 1, k plus 1 minus k is 1. And now what we're going to do is just kind of expand the brackets, because now if I do k plus 1 multiplied by what's outside the brackets, the k plus 1 and k plus 1 inverse are going to cancel, and I'm just left with k inverse. And then this minus k here is going to cancel with that k there, so I'm just left with minus k plus 1 inverse, like so. So I can use this and put that in here to get that this k times k plus 1 inverse now just becomes k inverse minus k plus 1 inverse, like so. But now this is a nice telescoping series, because if you can't see it, let's just write out the first few terms. This is 1 inverse minus 2 inverse, plus 2 inverse minus 3 inverse, plus 3 inverse minus 4 inverse, and so on, up to 9 inverse minus 10 inverse, like so. And then we've still got this minus 9 times 10 inverse here. But what's quite nice now is most of the middle terms here will cancel. We've got minus 2 inverse plus 2 inverse, those will cancel. Minus 3 inverse plus 3 inverse, those will cancel, and so on. So all we'll be left with is 1 inverse minus 10 inverse. So this is congruent to 1 inverse, which of course is just 1. The inverse of 1 is 1, minus 10 inverse, minus 9 more 10 inverses, sorry. But 10 inverse minus 9 times 10 inverse is just going to be 1 minus 10 times 10 inverse. But 10 times 10 inverse, very conveniently, is just 1. So we've got 1 minus 1, which of course is 0. So we've got that this expression here, when we chunk through all the algebra and using Fermat's little theorem, is congruent to 0 mod p, which tells us that at n equals p minus 2, this guy here is a multiple of p, for p being bigger than or equal to 11, which is kind of what we wanted to prove. So cool, we've dealt with primes bigger than or equal to 11. We still have to worry about when the primes are 2, 3, 5, and 7. So let me clean up the whiteboard and we'll continue. Okay, so the next thing we need to do is worry about primes 2, 3, 5, and 7, and we'll do that in that order. Firstly, p equals 2. This guy here is always going to be a multiple of 2. It's always going to be even, and hopefully it's quite clear to see. This guy here, k squared plus k, is just k times k plus 1. Obviously, 1 of k or k plus 1 will be even, so when you multiply them together, you're going to get something even. Raised to the power of n, even, minus this guy here, even. Everything's even. You're adding up a bunch of even numbers. There's lots and lots of evenness going on. It's always going to be even. Great. It's always a multiple of 2, so that rules out m having a factor of 2, because if it did, this guy and m would have a common divisor of at least 2. Cool. What about the case p equals 3? This is a little bit more tricky, but still not too difficult. We can write this guy here. We're going to look at it mod 3, so it's the sum from k equals 1 to 9. K squared plus k is just k times k plus 1 to the n, and then this guy here is 9 times something, so clearly a multiple of 3, so that guy vanishes when we look at it mod 3. And of course this thing here, k times k plus 1 to the n, well, for most cases either k or k plus 1 is going to be a multiple of 3. The only times we have to worry about that is if k itself is 1 more than a multiple of 3, and thus k plus 1 is 2 more than a multiple of 3, then neither of these guys here are a multiple of 3. But that only happens in 3 instances, when k equals 1, in which case it's 2 to the n, 1 times 2 to the n. K equals 4, and we get 4 times 5 to the n. But remember, we're looking at this mod 3, so that will also be 2 to the n, because that's 20 to the n, and 20 is 2 mod 3. So then the only other one is k equals 7. So we've got 7 times 8 raised to the n, and again, that's going to be 2 to the n mod 3. But then we've got 3 lots of 2 to the n, and so of course that's going to be 0 mod 3, because it's 3 times 2 to the n. So case k equals 3 is also done. In fact, we've shown that this expression here is always a multiple of 2 and 3, when in fact we only need to prove it was true for a particular value of n. But I guess it's kind of straightforward to do it in the case for all values of n. For the case p equals 5, now we're actually just going to show that it's true for n equals 1, because that's nice and straightforward, and we're just going to kind of do that by brute force. So we're going to look at the case sum from k equals 1 to 9 of k squared plus k minus 9 times 10. And so in this case, n is 1. Like so, and we're going to look at this expression mod 5. So this thing here vanishes because this is just 90. Cool. So we're just left with this guy here, k squared plus k raised to the 1 is just k squared plus k. And now we can just use our standard formula for the sum of the first few k squareds, the sum of the first few square numbers and the sum of the first few integers. So this guy here is just going to be equal to a sixth times 9 times 9 plus 1 times 2 times 9 plus 1 plus a half 9 times 9 plus 1, like so. And the things that we're looking out for here is the fact that 9 over 6 is just 3 over 2. So 9 over 6 is 3 over 2. And this half here, this 3 times a half, is going to make this 9 plus 1, which is 10, is going to make it into a 5. So we've got 3 times 5 times 19. And in particular, that guy there is a multiple of 5. And hopefully it's clear to see that this guy here is a multiple of 5. It's 9 times 10 over 2, so 9 times 5. So this is also a multiple of 5. So this, all in all, is just going to be 0 mod 5 as well. Cool, so we've dealt with the cases p equals 2, 3, and 5, and that goes alongside the case p is bigger than or equal to 11. So what does that tell us? That tells us if we expect this expression here to be coprime to m for any value of n, then it must be that m has, when you look at m's prime decomposition, it can only contain 7. So if it is to work, if this guy here is to be coprime to m for all values of n, then it must be that m is a power of 7. So that's kind of a necessary condition on m. I'm now actually going to prove that that is a sufficient condition on m, i.e. if m is a power of 7, then it will be coprime to this expression here for all values of n. But before I do that, let me clean up the whiteboard. Okay, so I claim that the case where m is a power of 7 is sufficient. In other words, if you give me a power of 7, it's always going to be coprime to this expression here for any value of n. Of course, I've got to prove that. What I've done here is I've drawn up a table, and it's got the first 6 values of n, so 1 up to 6, and in the right column, it's got the corresponding value of f of n mod 7, where f of n is just this expression we've been considering this whole problem. So this has just been written, kind of computed and filled in by brute force or by using a computer, just plugging n equals 1 into this expression, looking at it mod 7, I get 2. Same for 2, 3, 4, 5, and 6, I get 1, 1, 3, 2, and 5, respectively. Cool, so this function here, f of n, is this expression here, but in particular, I'm going to look at what it gives me mod 7. So it's going to give me either 0, 1, 2, 3, 4, 5, or 6. And thankfully, for the first 6 cases, it's not 0, it's never 0, because if it was 0, my claim would be completely false. We want to prove that this is never 0, and to do that, we're just going to be using Fermat's little theorem, because remember, Fermat's little theorem says that a to the 6 is going to be congruent to 1 mod 7 whenever a is not coprime to 7. Whenever a is coprime to 7, i.e. a is not a multiple of 7. But in fact, we can do one thing before we use Fermat's little theorem and actually simplify this expression slightly, because we can actually take out 2 terms from the summation, because there are 2 terms in this summation which are going to be congruent to 0 mod 7 because they're multiples of 7, namely the case where k equals 6 and k equals 7. Because remember, k squared plus k is just k times k plus 1. So when k is 6, the k plus 1 guy is 7, and when k is 7, then k is 7, obviously. So I can take out k equals 6 and k equals 7 from this summation. So it's just the sum from k equals 1 to 9, but without 6 or 7 of the exact same thing, k squared plus k to the n minus 9 times 10 to the n. And again, I can take these 2 out because they're going to contribute 0, because I'm looking at this guy mod 7. And now what we're going to do is write out any positive integer as 6 times something plus a remainder. So every positive integer, n, can be written in the form 6 times L plus R, where R is 1, 2, 3, all the way up to 6. So one of these numbers here. And what I want to do is use what we've got here, this table here, to prove that f of n is not going to be 0 mod 7, and then that will solve my problem. So f of n is just this guy here, evaluated at n equals 6L plus R. So the sum from k equals 1 to 9, but k does not equal 6 or 7, of k squared plus k, to the n, which is just 6L plus R, minus 9 times 10 to the 6L plus R, like so. But now we can use Fermat's little theorem, because a to the 6 is congruent to 1 mod 7, and we're looking at this guy here, mod 7. So we know that because k squared plus k, because we've taken out 6 and 7, we know that k squared plus k is not going to contain a factor of 7, thus it's coprime to 7. So this guy raised to the power of 6 is just going to evaluate out to 1. So this thing here is congruent to this sum. I'm just going to ignore writing out this thing every single time. K squared plus k to the 6l plus r is just k squared plus k to the r minus 9 times 10 to the 6l plus r. But again, we can do the same thing. 10 to the 6 is going to be congruent to 1 mod 7, so is 10 to the 6l. So this is going to be minus 9 times 10 to the r, like so. So f of n is just this guy here, but we know r is between 1 and 6, and we've just got a table here, and we know none of these values here are ever 0, so we can write this thing here does not equal 0, or is not equivalent to 0, or not congruent to 0 mod 7. So that tells us that this guy here is never going to be a multiple of 7, and that means that if m is a power of 7, it will work, i.e. m is always going to be coprime to this expression here, regardless of the value of n. So the set of solutions to our problem, or the set of values of m which work, are the powers of 7. Anyway, I hope that solution has always sense, and I hope you've managed to follow along. Do check out my other solution videos as well, and if you're new to the channel, please do consider subscribing and also giving this video a like as well. Anyway, that is all for today. Thank you for watching. I'll catch you in the next one. Have a great day.